Looking out at the void tonight, I am haunted by a question most never ask. Just how cold is space? It is obviously colder than any winter on Earth. But the reality out here is far more extreme. This abyss is less than 3 degrees from the absolute lowest temperature possible, and it is everywhere. This cold breaks our everyday understanding of physics, warping what matter is and pushing reality to its strangest limits. By the end of our orbit, you and I will truly understand what temperature means in this darkness. It reveals where our universe is heading. Before we continue our orbit, if you love these cosmic journeys, please hit subscribe. It is a small gesture that helps us reach more curious minds. Now, let us address a common misconception. People back home imagine space feels like a deep freezer or Antarctica during a pitch-black polar night, or maybe the thin air where jets cruise. They scale up their instincts, assuming it is just incredibly freezing. They are right about the intensity, but wrong about the mechanics. Out here, cold operates by different rules. Heat is a traveler. It flows from warm to cool via 3 distinct processes: conduction, convection, and radiation. Conduction is what you feel touching a cold surface. Heat drains from your hand and into the object. Think of your fingers on ice or bare feet on stone floors at 3 in the morning. That is contact. Convection happens when a cold fluid, like air or water, flows past a warm surface and steals the heat. It is why wind chill feels so biting. Moving fluid strips heat from a surface and carries it away. But those processes require a medium to travel through. They need a solid, a liquid, or a gas. They require matter. As I look out my window, I see space has almost none. There is nothing. It is not a perfect vacuum. No such thing truly exists anywhere in this observable universe. But it is empty enough that the difference barely matters for my mission up here. 1 cubic meter out here averages just 1 atom. Your bedroom holds 27 million trillion in that space. Even the best vacuum chambers built on Earth still contain billions of atoms in every cubic meter. But interstellar space has only 1, and in the massive voids between galaxies, it is even less. In these enormous, near-empty bubbles that define our universe, the density is almost non-existent. In this crushing emptiness, conduction fails. There is nothing to travel through. Convection has nothing to work with. The cooling systems your body relies on, the ones that make winter dangerous, are useless in this vacuum. All that remains is radiation. And that tells a terrifying story about how cold the universe truly is. Everything above absolute zero radiates energy as waves. Your body is doing it right now while watching this. You are glowing in the infrared, invisibly shedding heat into the room around you at every second. Usually, the walls radiate back. That exchange determines if you feel warm, comfortable, or just plain cold. This is thermal radiation, and it is the only heat exchange that works out here in the void. Out here, my body would bleed heat into the dark continuously, with almost nothing radiating back to me. Yet, there is a faint warmth radiating back from the abyss, something that fills every corner of existence. It was found by accident in 1964 by 2 radio astronomers named Arno Penzias and Robert Wilson. They were at Bell Laboratories in New Jersey, working with a massive, horn-shaped antenna. They were measuring radio signals from our galaxy, but they kept hearing an irritating, constant background hiss. It was everywhere. No matter where they pointed that dish, the same noise returned. Constant, day and night. They checked everything. They even thought it was interference from New York City, 50 miles away. They ruled that out. Then they checked for every possible local radio source they could find. They even checked a nuclear test site. They finally found pigeons nesting in the antenna, leaving a mess. They evicted the pigeons, scrubbed the antenna clean, and went back to their observations. But the noise remained, identical in every direction, identical at all times. What they had actually stumbled upon was the cosmic microwave background radiation. This is the cold afterglow of the Big Bang. Light traveling since the universe was 380,000 years old, stretched by 13.8 billion years of expansion into a mere whisper of microwave radiation. That radiation is just above the coldest temperature allowed. And you and I are surrounded by it right now. It is everywhere out here. Every inch of this void is soaked in ancient light, hitting my suit from every single angle. This light registers at a temperature of 2.725 Kelvin. For those back home, that is negative 454.8 degrees Fahrenheit. or negative 270.4 degrees Celsius. That is the baseline for the entire universe. Not zero, not even absolute zero, but it is the closest the cosmos gets on a grand scale. And from where I am sitting, it is still falling. As space expands around me, that background radiation stretches into longer wavelengths, thinning out and cooling down more every single second. Eons from now, it will drop even closer to absolute zero. The universe is on a slow, one-way trip toward a cold, so hauntingly complete. It is so total that scientists call it the heat death, the moment when every temperature across the cosmos finally levels out. All energy will be spent, leaving the cosmos in a frozen equilibrium where nothing, and I mean nothing, can ever move again. But you and I are getting ahead of ourselves. To grasp how cold 2.725 Kelvin is, we need to talk temperature. Temperature is not a thing. It is not a substance or some fluid filling up objects like water in a glass down on Earth. It is just a description, a way to measure the average kinetic energy of every tiny particle moving inside a substance. It is about how fast they vibrate and jostle. Hot means fast. Cold means slow. Think about that for a second out here. When things get hot, atoms move fast, slamming into each other and passing that energy onto whatever they happen to touch. When things are cold, those same particles have slowed down. They are still moving, sure, but they are sluggish, drained of all energy. Anything above absolute zero is moving. At the heat of boiling water, molecules are racing at hundreds of meters per second. They collide billions of times every second. Pure chaos. Now, imagine your kitchen freezer back home sitting around 0 degrees Fahrenheit, or roughly negative 18 degrees Celsius. At that point, water molecules slow down enough to lock into the rigid structure of ice. But they are still moving, vibrating inside their frozen lattice. Even the most solid matter out here is not truly still. The colder it gets, the slower those particles crawl. There is a limit, though, a point where all that thermal motion just stops. No vibration, no energy, no heat. That is absolute zero. We call that 0 Kelvin. It hits at negative 459.67 degrees Fahrenheit, or negative 273.15 Celsius. This is not just a record low, it is the coldest temperature that can possibly exist. It is the absolute floor. Below that, there is nothing. Temperature loses all meaning. And out here, the universe sits less than 3 degrees above that floor. The whole range of liquid water, where all life you know exists, only spans about 100 degrees Celsius. That gap between iced tea and hot coffee feels huge. Yet, the universe sits within 3 Kelvin of total stillness. That is what I am looking at. That is the baseline of the cosmos. Not neutral, it is as cold as it gets. Now, you and I are about to find something even stranger. That temperature is not the coldest thing in space. Because that microwave background is everywhere, anything floating in the void is constantly soaking up some of that ancient radiation. It means objects out here are not at absolute zero. They are being kept slightly warm by the faint glow of the beginning. This 13 billion-year-old afterglow settles at about 2.7 Kelvin. But there are spots far colder than that. Massive clouds of gas and dust out there can actually shield their hearts from even that faint microwave background. Inside those shielded, compressed centers, the temperature can plummet all the way down to a single Kelvin. Take the Boomerang Nebula, 5,000 light-years from home. We have measured it at just 1 degree Kelvin. That is 1 degree above the absolute floor. It is actually colder than the empty space surrounding it. This happens because gas is exploding outward from a dying star. And out here, when gas expands, it cools. Those molecules are working hard, pushing against the expansion, losing energy, and freezing over in the process. We call it adiabatic cooling, and it drives that gas well below the temperature of the universe itself. It is the coldest, natural thing we know, a place where the bite of space reaches its most terrifying extreme. Our telescopes need this cold to function, truly. The detectors we use to see infrared are incredibly sensitive instruments. The gear used to map the background and find the first galaxies has to pick up whispers of light. Just one photon can trigger a signal. The catch? Any warm object, including me, emits its own blinding radiation. That includes the telescope and its electronics. If they are warm, they drown everything in a flood of thermal light. It completely washes out the signals we are looking for. To see the stars, these detectors must stay frozen. We have to cool those infrared eyes until their own heat signal basically disappears into the dark. As you and I look toward the James Webb Space Telescope, launched December 25th, 2021, remember, it is chilled to 7 Kelvin. My mid-infrared instrument operates at much longer wavelengths and needs extreme sensitivity. We have to chill its detectors below 7 Kelvin just to function. We manage this in two ways. First, we parked the telescope at the second Lagrange point, about 1 million miles away from Earth. I am facing it directly away from the Sun. From here, the Sun, Earth and Moon all huddle together on the opposite side of my view. A 5-layer sunshield, vast as a tennis court, is built from a specialized material called Kapton. It is layered with reflective aluminum and silicon, bouncing every bit of sunlight away from our delicate instruments. On the sunny side of that shield, the temperature reaches a scorching 230 degrees Fahrenheit. But on my side, the temperature plunges to minus 394 degrees. It is absolutely brutal. That is a 600-degree difference across just 5 thin layers of film. Second, our mid-infrared gear is cooled by a cryocooler. It is a mechanical fridge that actively pumps heat away from the detectors. All of this, the shield, the orbit, the cooler, it all exists for a single, haunting reason. We have to be cold to see. Out here, any bit of warmth is just blinding noise. The universe speaks in faint whispers, and you and I can only hear them in the absolute dead of the cold. Our James Webb Space Telescope is, quite literally, the coldest astronomical instrument we have ever deployed in the void. And it is built this cold because the ancient universe it is hunting is just as frigid. Light from the first galaxies traveling for 13 billion years has been stretched thin by the expansion of space itself. It hits my senses as infrared. To see those births, I need a tool so cold it barely registers on any thermometer. 7 Kelvin, just 7 degrees above absolute zero, is maintained by sunshields and mechanical fridges in this precise orbital design. All this is to catch the freezing afterglow of a universe that was once impossibly hot. Cold helps us elsewhere, too. Some of the most precise measurements of the cosmic microwave background were made from the South Pole, not just from my spot in orbit. At 9,300 feet above sea level, the South Pole provides a perfect mix of killing cold and total dryness. That makes it the best spot on Earth for microwaves. Down there, moisture is a wall that absorbs the signals we need. Air so cold it freezes the water out becomes a clear, transparent window for us to peer through. The South Pole is cold enough that the air holds almost no moisture. Their 10-meter telescope has mapped the very background of the cosmos. It mapped the cosmic microwave background with stunning precision. They chose Antarctica because its freezing breath makes the atmosphere vanish. Cold makes the invisible seen. It is not just our subject, it is the very lens that allows our observation to happen. There is another phenomenon in this freezing void that most people ignore, but we have been studying it for decades. They call it the Casimir effect. In quantum mechanics, there is no such thing as a truly empty vacuum. This empty space around me is not empty at all. It is teeming with vacuum energy and silent fluctuations. Physics tells me that fields never truly hit zero. They jitter and shake even when there are no particles present. Random waves flicker in and out of existence all around my station. We call these virtual photons. Back in 1948, the physicist Hendrik Casimir predicted what happens if you put 2 metal plates together in this void. The field between them gets restricted. Wavelengths longer than the gap between the plates simply cannot fit. But outside those plates, everything flows freely. This creates a strange imbalance in the energy pressing against them. That imbalance creates a real force, an invisible hand pushing those plates together. We call it the Casimir force. We finally proved it in 1997. The measurements matched the math with terrifying precision. This is not just a space curiosity. In nanotechnology, it actually makes tiny components fuse together like glue. More importantly, it reveals the truth of the void I am floating in. The cold vacuum of space is definitely not nothing. It is seething with activity. Ghost particles are flickering everywhere, and vacuum energy is constantly pulsing in the dark. Even in the deepest, most frozen reaches between the stars, far from any sun, space is never actually empty. It is alive with fluctuations that carry real energy. This power, spread across the universe, might be connected to something bigger. It could be dark energy, that mysterious force pushing everything in my view further and further away. We are still guessing, though. The numbers do not quite line up if they were one and the same. It is actually our worst prediction ever. There is a massive gap between our theories and what I see out here. Still, the connection is suggestive. This cold, empty void is not passive. It has its own energy and hidden structure. We do not understand it yet, but this vacuum energy might be ripping the universe apart. Now, let's talk about how you and I would survive in that cold. Out here, it is not some abstract physics lesson. It is about the brutal, concrete reality of what the void does to my body and my ship. I am essentially a thermal system. My metabolism generates heat like a 100-watt light bulb, struggling to keep me warm in the dark. Normally, I lose heat through conduction and radiation, but I must maintain my core temperature within a terrifyingly narrow, fragile range to survive. We are talking roughly 94 to 107 degrees Fahrenheit, or 34 to 42 degrees Celsius. If my core drops below 94 degrees Fahrenheit, hypothermia sets in. My brain starts failing, and my judgment simply evaporates. In those early stages, people often make lethal decisions like removing their clothes. We call this phenomenon paradoxical undressing. Coordination fails. Shivering, the body's last-ditch effort to generate heat, turns violent and then simply stops as my muscles give out. At 82 degrees Fahrenheit or 28 Celsius, the heart starts to fail. Life-threatening arrhythmias begin to take over. At 78 degrees Fahrenheit, the heart can stop entirely. At the other extreme, the very proteins in my body begin to unfold. Enzymes quit and cells die. My brain is hypersensitive to overheating too. Heat stroke can cause permanent brain damage in minutes. I only have a 13-degree Fahrenheit window, about 7 degrees Celsius, before the machinery of my life breaks down forever. Against a universe of billions of degrees, or the 2.7 Kelvin of deep space, that 13-degree sliver feels like nothing. It is an infinitely thin line. Maintaining that window requires continuous, active, and sophisticated engineering from my life support systems. If you were tossed out here without a suit, an experiment I hope we never see you actually would not freeze instantly. That is one of the most persistent misconceptions about space. You would not shatter like a glass dropped on a concrete floor. This vacuum is actually an extraordinary thermal insulator. There is almost nothing out here to carry your heat away from you. Cooling through radiation is slow. Other dangers would kill you much faster, and the process is as complex as it is rapid. Without external pressure, the gases dissolved in your blood would bubble out of solution. It is like the bends, but far more severe. Moisture on your eyes and tongue would vaporize immediately. It is a violent, terrifying shift for any biological system out here. The air in your lungs would rush out. Without oxygen being delivered to your brain, you would lose consciousness within 15 seconds. Brain death would follow within minutes. Even after you lose consciousness, your body would continue to shed heat through radiation. But it depends on your orientation. Are you catching the sun's glare, or are you hidden away in the shadows? In direct sunlight, your body might actually absorb more radiation than it loses. The real danger there is cooking, not freezing. In the dark, you would cool gradually. Well insulated by your own tissue and the vacuum, it might take an hour to cool significantly. The cold is not the immediate threat. It is the long-term condition, the relentless drain of warmth through radiation over hours and years. For my spacecraft, this is the engineering reality. Not a dramatic freeze, but a slow, continuous thermal challenge requiring constant management. My engineers do not think about dramatic freezes. They think in heat budgets, calculating the balance so we do not fry. They measure how much heat every component generates and how much each of our surfaces radiates back into the void. They must keep our electronics within their operating range across the full arc of an orbit. It is not glamorous, but it is vital. These questions determine if we live or die. Several spacecraft have failed simply because their thermal management systems could not cope. The Mars Climate Orbiter, lost in 1999, failed because navigation errors had already sealed its fate in the atmosphere. Throughout history, the brutal thermal environments of the outer solar system have claimed instruments on many of our most important missions. The Galileo probe was designed to survive a dive into Jupiter in 1995, one of the most extreme environments ever explored. It sent data for 57 minutes before the crushing heat and pressure melted it deep below the Jovian cloud tops. Thermal management past Jupiter is a nightmare. You cannot rely on solar panels when you are that far from the sun. The sun is simply too faint beyond 5 astronomical units to provide any real power for a ship like mine. Voyager, Cassini, and New Horizons all used nuclear power sources called radioisotope thermoelectric generators to stay powered and warm. These devices turn the heat from the radioactive decay of plutonium-238 into the electricity we need. They provide a steady source of warmth to prevent the spacecraft from freezing. That slow radioactive decay is like a nuclear campfire. This has kept instruments functioning where the sun is just a bright star. That is what it takes to stay warm out here. But you and I should consider a question most people never even think to ask about this cold, dark void. We say space is cold, 2.7 degrees above absolute zero. That sounds like a definitive statement about its temperature. We treat it like a simple property. But remember, temperature is a property of matter, of particles moving and colliding. In a gas, it measures the average kinetic energy of molecules. In a solid, it measures the vibration of atoms. In a vacuum with almost no particles at all, the reality of temperature is fundamentally more complex. Out here, in the vast interstellar void, there is roughly 1 atom per cubic meter. They have a temperature because they are moving, carrying pure kinetic energy. These particles dance with the radiation fields around them, but their temperature does not always match the chill of the cosmic microwave background we feel out here. Honestly, the kinetic heat of particles in some pockets can skyrocket, hitting thousands or even tens of thousands of Kelvin. It is a hidden, invisible fire. Even while the background radiation sits at 2.7 Kelvin, these particles stay hot. It is a deep, frightening paradox of the vacuum. A place that feels freezing, yet has particles vibrating at thousands of degrees. The secret is that out here, we measure temperature in sparse plasma differently. In a gas this thin, those atoms move with insane energy, but they are so lonely they almost never collide with anything at all. They cannot transfer that heat to my suit through conduction. That energy is trapped in tiny particles with absolutely nothing to bump into or exchange it with. This is the eerie subtlety of extreme environments. You have temperature from moving particles, and then you have the temperature of the radiation field itself. In this thin vacuum, those two things just do not touch. When we talk about space being 2.725 Kelvin, there is a catch. That is just the temperature of the radiation bath filling the void. If I leave an object out here to settle, it eventually matches that radiation. It eventually finds equilibrium. See, it is not the vacuum itself that is cold. It is the bath of ancient radiation soaking through every inch of this empty darkness. That distinction reveals a haunting truth. Temperature is relational. It is about how energy is shared. Out here, radiation is the only master. Temperature belongs to the light, not the matter. The universe has a temperature, sure, but it is just the glow of ancient, ghostly microwave photons. These photons are drifting everywhere around me. The final, fading echo of the Big Bang, cooling down over billions of lonely years. It is a strange, heavy thought, but it is real. Let us look at the void again. What really happens when you drop an object into this cold? This is where your intuition fails you. You might think if I tossed something out the airlock, it would freeze solid in a heartbeat. You would imagine a piece of metal or a human body would instantly hit the floor of 2.7 Kelvin, just snap frozen by the surrounding darkness. Frozen, as cold as the background. But that is not the reality. The reason takes us back to the weird physics of this place. Out here, the only way to lose heat is through radiation, and radiation is agonizingly slow. Take a shiny object far from any sun. It will eventually freeze, but it is going to take ages. It all depends on how big it is and how much light it reflects. It could take hours or even days to lose its heat. In the void, objects are thermally isolated in a way you cannot imagine. It is unlike anything back on Earth. It creates these terrifying paradoxical moments. Imagine being in orbit, floating in the glare of the sun. One side of me is baking in sunlight, the other facing the freezing void. These swings would melt or shatter any unprotected gear. This happens every single orbit. The sun-facing side of the station hits 250 degrees Fahrenheit. It is an absolute furnace out there. That is over 120 degrees Celsius. Yet the shadow side at that exact same moment plummets to negative 250 degrees Fahrenheit. That is negative 157 degrees Celsius. There is a 500-degree Fahrenheit difference between two sides of this station structure. It is not that space is just hot or cold. It is because radiation is directional. and there is no air out here to move the heat. Space cannot balance the heat like air or water does back home. There are no convection currents to carry warmth around my hull. No atmosphere is pressing against us. If the sun hits you, you cook. If you are in the shadow, you freeze. It is that simple. Between those extremes is the perfect insulator, the vacuum. Keeping us alive in this chaos is the hardest part of being an astronaut. We have massive radiator panels and thick insulating blankets wrapped around us. It is the only thing keeping this station from buckling under the stress. Ammonia loops pump coolant constantly, while heaters fight the shadows. If any of these systems fail, we are in serious, immediate trouble. It all runs invisibly, keeping my cabin livable while wild, deadly extremes rage just a few centimeters away, outside this thin metal hull. My spacesuit is basically a tiny personal ship. I am wearing liquid cooling garments right against my skin just to keep from cooking. Fans move air and layers of insulation trap my warmth. Without this gear, if I stepped into the sunlight, I would not last long. I would overheat in minutes. In the shade, I would freeze. Space does not just kill you with cold, it kills you with the brutal, unforgiving extremes. Now, let us look at what this extreme cold really does to matter. This is where physics gets truly haunting. Cold stops being a number on a thermometer and starts revealing itself as a destructive force. It changes everything. Back on Earth at 70 degrees Fahrenheit or 21 Celsius, metals feel solid and reliable under your hand. Their atoms are constantly vibrating and electrons flow freely. That is why they conduct heat and power so well in normal conditions. Atomic bonds stay flexible. You can bend them, hammer them, and shape them under stress without the whole thing just snapping. We call this ductility, the ability to bend without shattering. If you stress a warm piece of steel, it gives way slowly. It deforms. It might fail eventually, but it gives me a warning. I see it bending long before the final break. It might fail eventually, but it gives me a warning. I see it bending long before the final break. This transformation of matter under extreme cold is a fundamental rule of survival out here in the cosmic mystery. Cool metal enough out here and everything changes. At deep freeze temperatures, the atomic vibrations giving metals their flexibility just die away. The crystal structures get rigid, nothing like back home. Put pressure on this deep freeze metal and it won't bend, it shatters. It just snaps. Clean breaks happen with zero warning and no chance to react. We call it the ductile to brittle transition. It is not just an engineering note, it is a death sentence for machines. This shift has wrecked history. The most famous case is also one of the darkest. Testing the Titanic's recovered steel showed high sulfur levels. That made her hull incredibly brittle in the deep. Cold water made that steel snap. On the night of April 14th, the North Atlantic was a frozen trap. 1912 saw temperatures of 28 degrees Fahrenheit, 2 below freezing. At that point, the ship's steel did not just dent. It did not buckle against the ice. It fractured. It snapped in ways normal steel never would have. The hull plates cracked wide open. Water surged in through seams far faster than if the metal had stayed flexible. The ocean did not sink her, but the cold made it lethal. It changed the very nature of the metal. In the void, near negative 450 degrees Fahrenheit or negative 268 Celsius, metals become extraordinarily brittle. Our rubber seals need to stay soft. In this cold, they crack and crumble like old pottery. Grease turns to stone. Gases you breathe on Earth turn to liquid or freeze into solid blocks. Even the nitrogen that makes up most of Earth's air, a gas so stable and inert, becomes a strange beast out here. It turns liquid at negative 320 degrees and freezes solid at negative 346 in the deep solar system. Methane and carbon dioxide, things you only know as air, turn into hard, frozen ice out here. Down on Pluto, the ground is literally made of frozen nitrogen and methane. We breathe these as gases. On Pluto, they are rocks. That is why our ships need such intense thermal shielding. Look at the Voyager probes from 1977. They carry heaters just to keep their electronics alive in the dark. Without that heat, as they drift further from the sun's warmth, their instruments would simply die. Cold is not just an inconvenience. Out past the planets, it redefines the very essence of matter. Let us look at chemistry together. What the void does to atoms is the most chilling part of the journey. It leads to a place you would never expect. See, chemistry is entirely slave to the temperature. Reactions happen when molecules smash together to swap bonds. The speed depends entirely on how much heat you have. Chill it, and things slow. Freeze it enough, and the dance of chemistry just stops. You and I are just walking chemistry. Breathing, thinking, even healing it is all part of that molecular clockwork. Every thought in your brain is a chemical cascade, moving at speeds dictated by the warmth of your blood. Our bodies keep a steady 98.6 degrees or 37 Celsius because the proteins driving our life only work in that very narrow thermal range. If my temperature drops, my metabolism fails. My heart slows, my lungs lag, and my mind begins to fade. If your core drops to 86 degrees Fahrenheit or 30 degrees Celsius, the chemical reactions of your life effectively just stop. That is how the void kills. Not with a bang, but with a quiet halt. But there is a twist. In the deep dark, inside those molecular clouds near absolute zero, chemistry does something impossible. It changes. At 1 Kelvin, molecules do not have the energy to react the way we expect. They cannot collide hard enough to bond. Instead, they just drift, settling on tiny dust grains in the void. On microscopic bits of silicate and carbon, molecules pile up over millions of years out there. Layer by layer, frozen water, ammonia, and carbon monoxide build up on these drifting specks. And right there, in the deepest freeze imaginable, something absolutely incredible begins to happen. Quantum mechanics takes the wheel. At these lows, a ghost-like trick called quantum tunneling becomes our reality. Usually, particles need energy to jump over barriers to bond. Without heat, they are stuck. But out here, particles do not always climb. They tunnel right through the walls. The chance of tunneling drops as those barriers get larger. For tiny things like hydrogen, this tunneling is everything. It lets them move when they should be frozen. It keeps happening even where normal chemistry has long since died. Impossible reactions start to happen in the dark, tunneling through the freeze over eons of time. We have detected complex molecules in those cold interstellar clouds. Surprising complexity in the dark. Methanol, ethanol, formaldehyde, and simple sugar molecules like glycoaldehyde. Even traces of formic acid are floating out here. I see material ejected from comets, leftovers from the solar system's frozen birth. We have detected glycine in that dust. Think about it. An amino acid, one of the 20 building blocks for every protein on Earth, is preserved in frozen comet ice for 4.5 billion years. It likely formed through quantum chemistry on frozen dust grains in the ancient cloud. The void is not just dead silence. It is a slow, patient, quantum mechanical laboratory operating on a scale of millions of years. Those complex organic molecules eventually drift into new stars and planets as massive clouds collapse under their own gravity. The ingredients for life were not forged in the heat of a star's core, but in the freezing dark between them. The cold of space is not just a barrier. It might be the workshop where the pieces of life are assembled. Let us look at the temperatures we face out here. The range from the sun to the deep black is staggering. The surface of the sun sits at roughly 9,940 degrees Fahrenheit. That is the photosphere, the glowing surface I see from here. The corona, the sun's outer atmosphere, is a pearlescent halo visible during total eclipses, reaching temperatures of several million degrees Fahrenheit. This is an enduring mystery. By every rule of physics, the corona should be cooler than the surface, not hotter. Heat flows to the cold, but the corona is thousands of times hotter than the surface burning beneath it. We still do not fully understand the mechanism, despite decades of research and missions designed to study it. Moving away from the sun, the heat drops. Mercury, the closest rock, experiences the solar system's most violent temperature swings. With no atmosphere to hold the warmth, the sunlit side hits 800 degrees Fahrenheit, roughly 427 degrees Celsius. The dark side plunges to minus 290 degrees Fahrenheit. In just one rotation of the planet Mercury, which takes 59 Earth days, the surface swings over 1,000 degrees. But Venus is actually the hottest planet. It is not distance, it is the air. Venus has a thick carbon dioxide atmosphere that acts as a terrifying heat trap. Sunlight gets in, but the heat cannot escape. It is a nightmare of a runaway greenhouse effect. Surface temperatures reach 860 degrees Fahrenheit. That is actually hotter than the surface of Mercury at its peak. And unlike Mercury, this heat is uniform across the planet. Day or night, the greenhouse effect on Venus is absolute. Even the dark side stays boiling. Looking back, Earth sits at just the right distance with the perfect atmospheric composition. This keeps us in that narrow window where water stays liquid and the chemistry of life can actually happen. We see an average of 57 degrees Fahrenheit, but that hides some truly brutal extremes down there. At Vostok Station, I recall they recorded a surface temperature of minus 128.6 degrees Fahrenheit. Air that cold is a hazard to breathe. Unprotected metal held at that temperature becomes as brittle as glass. At the other extreme, Death Valley has reached 130 degrees Fahrenheit in the heat of a summer day. Earth's full range spans more than 250 degrees Fahrenheit between its most extreme recorded points. Mars averages minus 80 degrees Fahrenheit, though summer days at the equator might reach 70 degrees for a moment. But by midnight, those same locations are plunging back down to minus 100 degrees Fahrenheit. And at the poles in winter, the temperature drops to around minus 195 degrees Fahrenheit. It is cold enough for the air to freeze. The carbon dioxide we breathe out would turn into solid, dry ice. Passing Jupiter, the cloud tops hover at around minus 230 degrees Fahrenheit. But the interior is another story. Under that crushing atmospheric weight, the heat and pressure increase to unimaginable levels. We believe the core reaches temperatures of around 43,000 degrees Fahrenheit. That is hotter than the Sun's surface. Saturn's clouds are colder, at around minus 288 degrees Fahrenheit. Uranus, the sideways ice giant, shows cloud top temperatures of around minus 357 degrees Fahrenheit. Neptune reaches minus 393 at its clouds, the coldest planetary atmosphere we have found. This is a frozen world. Yet, Neptune radiates over 2 times more energy than it receives from the Sun. It has an internal heat source, a ghost of its birth 4.5 billion years ago, leaking into space. This means the planet is substantially warmer inside than those freezing cloud top numbers would suggest. Pluto orbits in the Kuiper Belt at an average distance of roughly 3.7 billion miles from the Sun. Its surface temperatures fall to around minus 375 degrees Fahrenheit. Pluto drifts through the Kuiper Belt, nearly 4 billion miles away, a frozen rock clinging to the edge of the void. Out here, temperatures range between negative 375 and negative 400 degrees Fahrenheit. The New Horizons craft that swept past Pluto in 2015 gave me my first close look at that frozen world. What I saw was startling. Not just dead rock, but a landscape of nitrogen ice plains and massive water ice mountains. I see a layered nitrogen-methane haze in the atmosphere. Cold does not mean the world is simple. At Pluto's temperatures, I watch chemistry and physics create structures of extraordinary variety and haunting beauty. Beyond the heliopause lies interstellar space, the boundary where the Sun's wind finally gives way to the true cosmic medium. At roughly 11 billion miles from the Sun, the background temperature I measure drops to that cosmic baseline, 2.725 Kelvin. That is negative 454.8 degrees Fahrenheit. Our solar system sits inside a warm bubble of particle density created by the Sun. Step outside that bubble, as Voyager 1 did, and you enter the biting cold of the true interstellar medium. The difference between our solar system and the surrounding cosmos spans a range that is almost incomprehensible to me. It goes from 9,000 degrees at the Sun's surface to nearly absolute zero in the void around me. A single star, a bubble of warmth surrounded by the universe's cold, but space is not uniform in its chill. Before we find the coldest spots in the universe, look with me at how alien this place really is. We tend to think of this system as the Sun's domain, a lit, energetic environment governed by our central star. For the inner planets, that is true, but the distance from the Sun to Neptune is nearly 3 billion miles. That is about 4.5 billion kilometers. Out there, the Sun delivers 900 times less energy than on Earth. 900 times. The solar intensity you feel on a summer day would be reduced to less than what I receive from a candle. The outer solar system is not just cold, it is black. Sunlight at Neptune is 900 times dimmer than Earth. It is still the dominant light source, but it is qualitatively different from the blazing sun I used to know. This has profound implications for any object drifting at those massive distances. Without sunlight, the chemical reactions that shape atmospheres slow to a crawl. The very air begins to freeze out. Gases condense, and ice becomes hard as rock. The outer solar system is a different kind of reality. The moons of the outer planets reveal this clearly. Titan has a thick nitrogen atmosphere and vast surface lakes. These are lakes of liquid methane and ethane, not anything I would recognize as a liquid back home. Methane is liquid there because the surface temperature is around -290 degrees Fahrenheit. At those temperatures, methane exists as a liquid just the way water flows on Earth. I see methane rain cycles and methane rivers cutting deep channels into the frozen, icy landscapes. There are methane deltas meeting liquid shorelines. It is a world with familiar geography but utterly alien chemistry. The Cassini spacecraft, which orbited Saturn for 13 years, mapped Titan with radar because the moon's thick haze hides the surface. It found a world where hydrocarbons do what water does on Earth. Cold has made the familiar terrifyingly alien. Triton, Neptune's largest moon, has surface temperatures around -391 degrees Fahrenheit. This is near the very bottom of the temperature range for solid surfaces anywhere in our solar system. And yet, Triton is not a dead world. I can see active geysers erupting there. These are not volcanic geysers erupting heat, but nitrogen plumes powered by the sun. Triton is coated in transparent ice. Sunlight, even as pale as it is at Neptune, penetrates that ice and warms the darker material underneath. That slight warming sublimates the nitrogen ice from below, and the pressurized gas erupts through the surface, shooting dark dust particles several miles into the atmosphere. These active geysers are powered by sunlight, so faint it delivers less energy than a household LED bulb. This is what extreme cold does. At these temperatures, the tiniest energy inputs can drive massive geological activity. Because the threshold for nitrogen is so close to the ambient temperature, even tiny warmth triggers an eruption. Cold doesn't mean static. It means being poised on an edge, where the smallest push causes extraordinary things. There is something called the cosmic web. When you and I map galaxies across the universe, it is no fog. As I gaze out from this station, galaxies aren't just tossed around. They form a terrifying, grand pattern. These arc-them universes cluster into groups, then into massive, haunting superclusters. They connect along filaments, monstrous rivers of gas and stars, stretching across millions of light years. In between those filaments lie the void's vast, hollow pockets where almost no light reaches me. These voids span hundreds of millions of light years across, swallowing most of the visible universe's volume. The trace amounts of gas inside these pits are frozen, chilling near the cosmic microwave background. Sometimes it is slightly warmer, but from out here, those voids look cold, empty, and utterly dead. The universe out there covers 415 billion light years. Each light year is nearly 6 trillion miles. That scale is impossible to grasp, and most of it is just this freezing, lightless, empty nothing. The beauty we admire, the stars and clusters, occupies only a tiny sliver of all that space. Everything else is just a freezing void. This is the universe's true, cold face staring back. Forget the glittering stars. They are just the exceptions. The dark and the cold are the real masters. In those deep hollows, the temperature is dictated by the ancient echo of the cosmic microwave background. It is just 2.725 Kelvin. No starlight warms it. No suns exist to burn there. No gas, no heat, just a radiation field and the ghost of a light from the beginning. Even that ancient light is fading. Every 100 million years, the temperature drops just a tiny bit more. As space stretches, the wavelengths pull apart, and the voids around me grow even colder. The whole universe is freezing, and in those voids, there is nothing out there to stop it. No local fires, no warmth to fight back. Just a slow, lonely drift toward absolute zero. Let's look at one more mystery. The cold makes possible something that decides the fate of all matter. Black holes. We've talked about them, but their thermal physics is far more disturbing than I realized. For a long time, we believed black holes were purely cold, thermodynamic dead ends. They swallowed matter and light, letting nothing escape. Their horizons were the perfect, hungry traps. They were the ultimate dark bodies. But in 1974, Stephen Hawking proved we were wrong. By mixing Einstein's gravity with quantum mechanics, he showed these giants are not actually perfectly cold. They bleed. Quantum effects at the point of no return cause black holes to emit thermal radiation. This radiation is impossibly faint, but it is there. We call this ghostly leak Hawking radiation. A black hole's temperature depends entirely on its mass. The bigger they are, the colder they get. A black hole with the sun's mass is 6 times 10 to the power of -8 Kelvin. That is 40 million times colder than the background radiation of space itself. Think about that. A giant like that actually drinks more energy from the universe than it leaks through Hawking radiation. To lose mass, the entire universe must first cool down below that black hole's Hawking temperature. This takes an eternity of expansion. Finally, even solar mass black holes will start to bleed more energy. Then, the evaporation begins. As the hole shrinks, its temperature starts to climb higher and higher. Smaller means hotter. As it vanishes towards zero mass, its heat screams toward infinity. Scientists think those final moments end in a violent explosion, a burst of raw, high-energy particles. It is a journey from the coldest thing in existence to a final, blinding spike of heat. Black hole physics weaves reality together in ways that are both beautiful and terrifyingly confusing. But there is a problem. The information paradox. Drop an object in, and its story seems lost. Every quantum state of every particle that made that object seems to vanish into the dark. If the black hole evaporates completely, everything that ever fell in is just gone. That breaks the most basic rule of quantum mechanics, that information can never truly be destroyed. Where does it go? We do not know. Even Hawking changed his mind about it for decades. Today, we suspect the information is hidden in that Hawking radiation, scrambled but still surviving. But the math is still a mess. Black hole heat is where our deepest secrets are buried. Up here, I wonder how data survives that lethal cold, or how quantum rules bend near crushing gravity. I ponder what stays when the final black hole vanishes, leaving only a ghost of cold, thin radiation. These aren't just thoughts for my long shifts. Our brightest minds are hunting for these answers right now. This biting cold just outside my glass, this primal freeze, is the core of every single mystery out here. My sensors find places that push boundaries even further, exposing strange truths about how matter and heat behave. You and I remember the Boomerang Nebula's 1 Kelvin chill. But there is another cold, moving on a far longer clock. Imagine a star 8 to 10 times larger than our sun finally burning out and collapsing into itself. The shell erupts in a supernova, while the core is squeezed into a 10-mile-wide ball, a neutron star. During that collapse, the core hits 100 billion degrees Fahrenheit. It is the hottest point since the beginning. It creates something so dense that a tiny teaspoon of it would weigh 1 billion tons back on Earth. But even these giants cool. Within minutes, they bleed energy through neutrinos, stripping away their heat at a terrifying rate. After thousands of years, they drop to millions of degrees. Still searingly hot, but undeniably getting colder by the minute. Billions of years later, they freeze more. Old stars with dying magnetic fields slowly leak their remaining warmth into the void. In the far future, across quadrillions of years, even these stubborn neutron stars will have lost almost all their warmth. They merge with the frozen background. Like me, out here, everything in this cosmos follows that same lonely path. Everything freezes, everything drifts toward the dark. A single rule of physics binds all of this together for us. It is a concept so vital that it might be the most important rule in science. We call it entropy. Simply put, entropy measures disorder, just how many ways the pieces of a system can be scrambled and rearranged. More deeply, entropy is why my mission clock only ticks forward. The second law says that disorder must always grow. Chaos expands. The universe slides from order to mess, from hot to cold, from intense energy to a thin, flat nothing. This isn't just a trend, it is a law, the most reliable and unbreakable rule in the entire physical realm. Heat only bleeds from hot to cold, never the other way. Out here, I see every temperature difference slowly smoothing out. All structures crumble. The universe is falling toward total chaos. We call this final state of maximum entropy the heat death. It isn't a violent death. No blast, no crash. Just the slow, inevitable consequence of the universe, following its own rules. This is just the second law playing out. Every gap in temperature is a precious fuel tank of usable energy. Burning stars are gradients, hot plasma fighting the cold void. Life back home survives on the gap between sun and space. That is 9,000 degrees meeting the 2.7 degree chill. Every engine we've ever built feeds on that difference. My own heartbeat and thoughts run on these gaps. As the cosmos ages, they vanish. Stars burn out and go dark. Entire galaxies dim. Even black holes, holding the weight of millions of stars, start to evaporate through strange quantum leaks. This is Hawking radiation. A sun-sized black hole has a temperature around 60 billionths of a Kelvin, nearly absolute zero. That is colder than the void itself, so the hole actually swallows more energy from the background than it emits. But as the cosmos cools more and the background drops, the tide turns. The black holes start losing energy faster. They vanish over 10 to the 67th years, far longer for the supermassive monsters lurking in the dark. This happens long after the final star fades, long after the last neutron star has cooled into the frozen background, long after galaxies drift apart and stars die. Eventually, even the holes vanish, leaving the universe filled only with radiation. No gaps in temperature, no power left to use. The heat death has reached its final, freezing conclusion. The temperature out there will look exactly like absolute zero. Not quite, but close enough that we couldn't tell. Physics might not allow a true absolute zero, but the cosmos will get as close as theoretically possible. It will be colder than any place I could find today. Scientists say this end state is incredibly far off. We are looking at 10 to the 100th years away. That is a 1 followed by 100 zeros. Our current age is 13.8 billion years, a number that only has 10 digits in it. 10 to the 100th has over 100 digits. It makes our entire history look like a blink. My words can't truly capture it. But the path is clear. The universe is freezing and has been since the start. At the start, we were smaller than a proton and hotter than any known number. We've been cooling ever since. You and I live in a brief, warm era, but the temperature is dropping with every second that passes. We are living in a tiny, glowing sliver of time between a fiery birth and the dark. These stars I see, they are just temporary. They are flickerings in a cosmos that is, in the long run, slowing down and cooling toward a total, final silence. To grasp the freezing void ahead, you and I have to look back at the inferno where it all began. The Big Bang was not some ordinary explosion. There was not even any space out there for it to explode into. It was the birth of space and time themselves. In those first split seconds, the entire universe was impossibly hot and packed tight. Temperatures hit over 10 to the 32nd power Kelvin, the Planck temperature. We think that is the absolute limit of heat before our current understanding of physics just stops making sense. Past that point, quantum gravity takes over, and every theory we have completely falls apart out here in the deep. We have no clue what happened back then. Our science cannot reach it. From that wild start, everything expanded and cooled fast. Within 1 second, it dropped to 10 billion degrees. Still hellish, but nothing like what it was at the very start. Early on, the cosmos was a thick, scorching soup of protons, neutrons, and strange particles we hardly ever see out here now. By minute 3, it hit 1 billion degrees, finally cool enough for particles to bond into the very first light elements: hydrogen, helium, and a bit of lithium. That is Big Bang nucleosynthesis, the source of almost every atom in the stars today. Every atom in your body, the water you drink, and the stars burning fuel above me, it all started right there. All of it was forged in those first 3 minutes as the universe cooled from its original primordial fire. For the next 380,000 years, the universe kept cooling, but stayed completely opaque. It was so incredibly dense that light could not travel more than an inch before slamming into a sea of charged particles. The universe glowed with fierce light, yet you could not see through it. Then, at that 380,000-year mark, it cooled. It plummeted down to about 5,400 degrees Fahrenheit. At that specific point, electrons and protons finally joined up to form neutral hydrogen. Suddenly, the fog lifted. The universe became transparent. Light was finally free to move through the void. For the first time, light could cross the cosmos. Those photons have been traveling for 13.8 billion years now. It was stretched by expansion from visible light to microwave wavelengths, cooling all the way from 3000 Kelvin down to just 2.725. Every photon detected back in 1964 had been on the move for 13.8 billion years. Each one carries a ghost of the moment the universe cleared up, and light first started racing through the dark. That background cold we measure is not just a number. It is the diary of a journey across the entire age of time. When you look up at the stars tonight, you are peering through a universe soaked in that ancient, invisible light. It is microwave radiation, so our eyes miss it entirely, but it is everywhere, in every single cubic inch of the space between us. This is the frozen afterglow of creation. But then came a time we call the cosmic dark ages. It began 380,000 years after the start, right when things cooled enough for the fog to clear. Matter finally settled down, turning the universe from a murky soup into something clear. But clear does not mean bright. Transparent is one thing, but lit is another. The universe was clear, but it was pitch black and freezing. There were no stars yet, no galaxies. Nothing but the fading, lonely glow of the background radiation itself drifting through the deep void. Huge clouds of hydrogen and helium just drifted in the dark. Slowly, gravity started pulling those shadows together. Thick regions grabbed more gas, and things began to collapse. Over tens of millions of years, the first structures took shape. Dark matter halos were assembling from the tiny ripples left over from the very beginning of everything. Regular matter, hydrogen and helium fell into those dark traps, heating up as it tumbled toward the center. Finally, at the heart of the densest piles, it got hot enough to ignite. The very first stars were born. They probably sparked up about 100 or 200 million years after the Big Bang, but we have not seen them yet. They are too far away, and their light has been stretched too thin by the expansion of the universe to see. We have the James Webb Telescope out here looking. Those first stars were nothing like the ones we see now. Made of pure hydrogen and helium, they were absolute monsters, hundreds of times more massive than our own sun. Massive giants like that burn fuel fast. They lived maybe 1 million years before they went out in a bang. Supernovae sprayed the first heavy elements carbon, oxygen, and iron into space, seeding the clouds so the next generation of stars could grow. All of this unfolded while the universe froze, going from that initial clear glow to the first sparks in the dark. You and I have to realize, the Dark Ages were not empty. They were a slow, cold assembly of gravity, working in the shadows. Today, you and I are watching warmth organize itself into layers against the freezing black. I imagine that transition from uniform cold to the first islands of light. We call it reionization. When those first stars ignited, they flooded the void with blinding ultraviolet radiation. That energy tore through neutral hydrogen, stripping away electrons from atoms that had only just formed. Everything became ionized again, not all at once, but in glowing bubbles surrounding every new galaxy. Those bubbles formed massive spheres that merged over millions of years until nearly all the hydrogen changed. 1 billion years after it all began, the Dark Ages finally died. Light had won. The stars were out, but the freezing grip of the void never left. It is still there. Stars do not actually warm the universe. They are just tiny, brilliant sparks, fighting an ocean of cold. Billions of light years of nothing but ice and shadow. That is how it has always been. It remains the same today. Starlight is just scattered warmth, separated by terrifyingly vast distances of cold. If you average it all out, the temperature of this entire universe sits barely above absolute zero. Every star I see is a lonely island, every galaxy a chain, and the cold rules everything. It is ancient and absolute. But look, join me closer to home, because there is a secret here. There is one thing people miss about the vacuum. The cold does not just kill, it preserves. You see it in your freezer. Cold slows down the chemical decay that eventually breaks everything apart. Museums use it to save history from rotting. We freeze biological samples to keep them perfect. Out here, that preservation happens on a scale you cannot imagine, keeping things perfect for eons. I look at comets and see ancient debris, irregular shells of ice holding primordial chemicals. They were born 4.5 billion years ago, back when our solar system was gas. They spend almost all of their time in the freezing outer reaches, drifting way beyond the Kuiper belt. Their insides have not changed since the dawn of time. Cold has held them for billions of years. But if a comet gets bumped into an orbit near the sun, it finally begins to thaw. The ice turns straight to gas, we call it sublimation, creating that brilliant coma and tail I see. The core stays frozen solid. We study them because they are perfect time capsules of our history. The molecules in that ice are the same ones present when Earth was still just forming. The European Space Agency sent Rosetta to orbit comet 67P from 2014 to 2016. They dropped a lander on the surface and found glycine drifting in the gases. Glycine is a building block of life, kept safe in that ice for 4.5 billion years. It was born in the deep freeze of molecular clouds, then locked away for our entire history. That is the true power of the void. It does not just kill or stop time. It preserves things for eons, far longer than life has existed on Earth. Look toward the Oort cloud. It is a massive shell of ice surrounding us, 100,000 times further out than the Sun. The edge of that cloud is nearly 2 light-years away, halfway to our nearest stellar neighbor. Those icy rocks started here, near us, but were kicked out into the dark billions of years ago. Floating at 2.7 Kelvin, they have stayed perfect for 4.5 billion years. Cosmic rays hit their skin, but their cores are frozen in time, exactly as they were at birth. If I could reach them, which I cannot, I would find the most pristine material in the universe. They hold chemistry from 4.5 billion years ago, created before our sun even existed. Even the Voyager probes, our fastest machines, would need 300 years just to reach that edge. It would take tens of thousands of years to cross that cloud. This cold is not a wall. It is a patient, vast archive. Let us pause here together and consider the weight of that. We talk about the chill like it is one thing, but the cold has its own geography. The sun's surface is 9,940 degrees, while the corona hits millions. We stay in the warmth where water flows, while the rest of the cosmos remains at absolute zero. Out here, molecular clouds drop to 1 Kelvin. Even the coldest labs on Earth reach 100 picokelvins. These aren't just numbers on a dial. They represent entirely different physical worlds, governed by strange, alien rules. Inside the sun's corona, matter turns to plasma. Electrons and ions rip apart, dancing in ways solids and liquids never could. Down in the photosphere, some atoms ionize while others wait. This creates the light patterns we use to decode the stars. We use this to see what stars are made of. Back home, molecules bond, chemistry flows, and life finally happens. Floating past the outer planets, chemistry turns exotic. At 1 Kelvin, quantum tunneling takes over, moving atoms across frozen surfaces. At 100 picokelvins, quantum laws go big. I have realized the universe does not have just one cold. It has many colds. Each one reveals a terrifying new face of matter and energy as we look deeper. Watching how physics shifts between these states is chilling. It is one of the most profound things we have ever discovered. We call these phase transitions. They are far deeper than just water freezing or boiling back on Earth. Think of the moment plasma turned to gas, 380,000 years after everything began, or the shift to superfluid matter in liquid helium at 2.17 Kelvin. Matter just starts flowing differently. Metals becoming superconductors at a few Kelvin. These are echoes of transitions that happened when the universe was just born. I imagine the electroweak force splitting in two as the temperature dropped below 10 to the 15 Kelvin. Reality itself was being forged. This happened in a mere heartbeat. Before that, the strong nuclear force broke away at temperatures even more extreme than that one. Our entire history is just a story of the universe cooling down. Each drop in temperature created a brand new physical world. Every stage opened new doors for matter. The biting cold I see now took 13.8 billion years of transitions to create. Each one changed what matter could do. They decided what structures could even exist in this vast, dark space. I am drifting through a phase where stars burn and life takes root. But we must realize this is not the only phase. The universe won't stay like this forever. But for now, this is where you and I find ourselves. Knowing we belong to a brief era that allows complexity is heavy. It changes how I see everything out here. There is a deeper question. We started with the idea that cold is familiar. You think you know what it feels like. But real cold, universal cold, is nothing like a winter morning back on Earth. It is something far more mysterious and terrifying. This cold predates the sun. It will be here long after every star in my view has finally burned out. It fills the vast majority of space already. Soon, it will be all that is left of our universe. That 2.725 Kelvin background hum, that is exactly the target where everything is slowly cooling toward. Something profound emerges from that. Life only exists because of a simple temperature gap. The sun is 9,000 degrees. Out here, it is minus 455 degrees Fahrenheit. Exactly. That massive gap drives the energy that powers Earth's weather and moves the oceans. It is a cosmic engine. It keeps biology running. But realize this, we do not actually run on the sun's heat in a direct way. We survive on the difference between solar heat and this dark void. Without the cold, the sun would be useless. Without the universal cold as a backdrop, energy would have nowhere to go. This freezing void is exactly what makes warmth meaningful. Take away the cold, and everything equalizes. Chemistry stops. Life needs a cold place to flow into in order to survive. This cold is not separate from our story. It is part of the engine. I know this defies every basic human instinct. We usually think of cold as the killer, the threat, the hostile environment that wants to end us. From my view out here, cold is not the enemy. It is a necessary partner for our very existence. Energy gradients only exist because there is a cold place for all that energy to travel toward. This lets solar fusion do something useful. Otherwise, the heat would just trap us in a closed system. Earth's entire energy budget comes from the contrast between the sun and the cold void I am looking at now. Without the cold, there is no contrast. Without that contrast, the universe would just drift in a total thermal equilibrium. In that equilibrium, nothing ever happens. Nothing builds, nothing reacts, and absolutely nothing ever lives. Paradoxically, the cold of the universe is why anything here exists at all. There is another way to see this. You and I need to look deeper into what this cold represents. Ludwig Boltzmann died in 1906. He spent his whole life trying to understand the nature of entropy. He proved that entropy, that measure of disorder, is really just a statement about basic probability. Out here, low entropy is a freak accident. High entropy is just the cosmic default. The universe slides from order to chaos, from heat to frost, simply because the dark has more ways to be cold. It is not drifting toward the freeze because the cold is somehow better or more fundamental. It moves toward the freeze because scattered, messy states are just more likely than the hot, structured ones we call home. By the brutal math of probability, the cosmos will spend nearly all of its time in its most likely shape, and that shape is freezing, empty, and uniform a state of near-perfect chaos and maximum entropy. This means everything I see, the stars, the planets, and even us, are just statistical anomalies in the void. We are nothing more than improbable ripples in the universe's preferred state of icy stillness. We don't exist because the void loves complexity, but because space is just so massive and incredibly old. In a system this big and this old, even the most impossible arrangements are bound to happen eventually. I look at our solar system and realize it exists only because one cloud of dust happened to collapse into a star. We sit in the habitable zone of that sun because a dozen different coincidences all happen to align at once. Our distance from the sun and the pull of the gas giants keep our orbit steady in a very unstable universe. Even our moon keeps this world from wobbling, creating a stable climate that actually allows us to breathe. Life crawled out of the dirt, sustained by the heat of a star against the freeze of the void. We are the fluke the cosmos accidentally produced. And understanding that isn't depressing, it is actually quite chilling. It brings clarity. It means this planet, this warmth, and our very lives were never guaranteed to us. My ability to stare at the stars and wonder isn't some grand design. It is just a roll of the dice. We are a flicker, a brief moment of structure in a reality that is mostly hollow, cold, and empty. That impossible math is what gave us art, science, music, and this desperate human need to understand our place. Every memory you have, every person you love, and every thought is just a result of a temperature difference. It all happens because the sun burns and space freezes. In that gap, chemistry found a way to build itself. That is the truth about the deep freeze of space. It is not just a hazard that kills you without a suit. It is not just a barrier to travel. It is the universe's baseline, and all warmth represents a temporary departure. We live on the exception. We are the exception. But in billions of years, the sun will eventually go dark. The world will freeze. The exception will vanish, and the cold will reclaim everything it once owned. It is 2.7 degrees above absolute zero and dropping. Out here, entropy always wins the war. Heat always bleeds into the dark until everything levels out into the final, frozen silence of its end state. Yet, here I am maintaining warmth, building dreams, and asking questions about the very void trying to swallow me. It is vast beyond any human measure or comprehension, and it will win. Every single star will die. Every spark of warmth in the cosmos will eventually fade into the expanding nothingness, but not today. For now, in this tiny window of time, the sun burns, I stay warm, and we try to make sense of the dark. We fragile, temporary sparks of chemistry look up and try to understand the infinite. That is what is truly remarkable.